Okay, so hello everyone, I'm Susanna, and the plan for today is to dive into the concept of roles in a network. So a quick overview of what we are going to cover today. We will start with a brief introduction to give the big picture of the concept itself. Then I have some examples because I am the first one to say that the concept might be not super intuitive because it's on an abstract level, I would say. So I tried to include as many examples as possible so you can see what I'm talking about in practice. Then we will cover the classical point of view on graph clustering, which is communities. I'm going to give a quick definition in order to compare communities to roles, which are the next section. And we're going to formalize the concept of roles, but also go through the main categories of role discovery. Then I have a section on application, which basically is a short list of applications where both communities and roles can be applied, but with some tips and tricks on which cases are more prone to be solved with the one or the other. And then a quick conclusion to wrap up the take-home messages. And if you have any question or if you would like to comment something, please interrupt me anytime, no stress at all. Okay, so let's start. Since we're going to talk about networks, I included here a quick definition where networks are a set of nodes with some pairs connected by edges. And just to put things clear, we use the term graph to refer to the mathematical model, whereas networks are more the practical version of the graph, in the sense that nodes represent real-world objects, and the edges are there to encode some kind of relationship between these objects. Okay, so as I was saying before, there are two different perspectives on networks. On the one hand, we have communities that are kind of well-known and popular. But what we're going to cover today is a new, fresher perspective, which is the one of roles. Basically, communities and roles are two sides of the same coin. So they are different but complementary. And for this reason, they are equally important in the sense that there are some tasks which are easier to solve with communities, but there are also some other tasks that require the use of roles. And roles are kind of less intuitive because they are on a higher level of abstraction compared to communities, but we're going to define these differences later on with some formalism. Then we have the problem of graph clustering that, according to this dualism between communities and role, can take two different forms. So on the one hand, we have community detection, and on the other hand, role discovery. But formally, they are the same problem of dividing nodes into groups according to some criteria. What changes is the objective. So some examples to make things clear. Let's say we have a company or even a university, and there are some employees in this company, let's say managers, developers, and of course everyone has a job title. But in practice, what happens is that there are departments, which means a group of people that work frequently with each other. And as I was saying before, in the same way that it is possible to partition a graph according to communities or roles, in this case, which is basically an organizational chart, for example, it is possible to classify employees according to which department they belong to, or which is their job title. So let's see that we have the row network, the black one, and we want to find the communities. What we do is we run a community detection algorithm, and what we would like to get as a result is the colored graph that you can see here, where different colors represent the different communities. So we have two departments, which with a CEO, I guess, in the middle. And similarly, if we start from the same graph, but we are interested in role discovery, we will end up with something a little bit different, because as you can see here, colors do not represent communities, but roles. So we have the red nodes that most probably will be some kind of management, whereas the developers, let's say, are the blue nodes that have some connection with product managers, or HR, or administration. So now that we have a glimpse of what the communities and roles are, I would give some more formal definitions. So there are many definitions of communities, but the most modern one, according to a really nice survey by Santo Fortunato, is that communities are a set of nodes which are more likely to be connected to nodes within the same communities, and unlikely to be connected to the other communities, which translates back to the classical formulation that the communities are a dense set of roles that are well separated from the others. And from this perspective, community detection is the task of dividing the nodes in a graph according to which community they belong to. I'm not going to cover all different categories of community detection algorithms that are out there, because there are a lot. But as a rule of thumb, the idea is that you want to maximize the internal connectivity, so the number of edges between the nodes inside the same community. And at the same time, you want to minimize the connection between the nodes belonging to different communities. Now, let's move to the concept of roles, which is the main focus of this presentation. So formally, roles are a set of nodes in a graph that are structurally similar. And I'm going to explain what I mean by structurally similar. But I would also like to point out that roles have been around for quite some time, but just in recent years, they received a lively interest, whereas at the beginning, they were mainly confined to the field of social network analysis, because, I mean, it's easy if you think of Instagram to point out that, for example, influencers are a role, but in the same way, there are trolls in Twitter and so on. But since this definition of roles that was used in the beginning is kind of related to social sciences, we need a definition that is more general and can be transferred between different fields. And what I would like to do is use some examples to build step by step what does it mean for two nodes to be structurally similar. So let's start with structural equivalence. We say that two nodes are structurally equivalent if they are connected to the same neighbors. So for example, in this graph here, we have the nodes from 2 to 7, so the green ones, that are structurally similar because they are connected to the same node 1 here in the middle. Of course, this definition is not really practical because it's very strict. So let's make it a little bit more useful for practical purposes. And so we move to regular equivalence. In this case, we say that two nodes are equivalent if they are connected to role equivalent neighbors, in the sense that two nodes have the same role if they are connected to neighbors that, in terms of composition from the point of view of roles, they are the same. And once again, since this concept is kind of abstract, let's make an example. As you can see here, we have two nodes, 1 and 13, which are not connected to the same nodes, but they have the same role because all the green nodes are equivalent to each other. So what happens is that 1 and 13 basically exhibit similar connection patterns to other roles. Now, we like this definition a little bit more than the previous one, but still it's kind of strict in the sense that it does not consider that in reality there is noise, there are errors, and so on. So for this reason, what is the most popular definition of roles nowadays is that two nodes belong to the same role if they are structurally similar. Which means that they are connected to neighbors that are not equivalent as before, but similar. And this definition allows us to have some irregularities in the data. So in this graph here, as you can see, node 1 is the same as before, but 13 has one more friend now. And moreover, we have this situation where the friend of my friend is also my friend. So there is a stronger connectivity here, but still we see some similarities between 1 and 13 in the sense that they act as hubs, which means nodes that are like kind of popular. Okay. According to this definition, we can go back to the graph clustering problem that I was mentioning before, but in this case, our objective is to divide the nodes according to their role, and in such a way that in the end, we end up with a set of nodes that are structurally similar to each other, as happens here in the organizational chart we were looking at before. And there are a lot of role discovery methods, not as much as community detection, but still it's possible to do classification of these methods. And the three main categories that are out there these days are graph-based methods, feature-based methods, and then a category which is like in the middle and as such is called hybrid methods. The main difference between the two main categories is that while graph-based methods operate on the graph itself directly, feature-based methods want to be more scalable by operating on the graph indirectly via features. But I would like to start give a brief overview of graph-based methods, because at least in the beginning, when we were talking about social network analysis, these methods were the ones that were used the most. And the main example of graph-based methods are block models. You might have heard of it because they are also used to generate random graphs. But formally, the objective of block models is to manipulate the adjacency matrix that represent the connection between the nodes in a graph in such a way that all the nodes inside the same block or role are equivalent. And the very first methods were more connected to the concept of structural equivalent nodes, but there has been some development in the direction of stochastic block models that allow for a more flexible definition of what role means. But in general, the main idea is that similarly to what we were saying before, two nodes belong to the same block or role if they exhibit similar connection patterns to the other blocks that are there in the graph. And one really nice thing that has been done with block models is to basically substitute all the nodes in a block with a supernode. And in this way, it is possible to highlight the relationship that occur between roles. And some of you may say that the block models seem more related to the concept of community. But I have an example here, which is really nice, because as you can see in the graph with nodes 1 to 9, there are three groups, red, green, and blue. And while red nodes and blue nodes are also connected to each other, so they form a community, this is not true for green nodes because there are no connection between green nodes, but they are similar because they all have incoming edges from red nodes and outgoing edges to blue nodes. And I hope these examples helps clarify the fact that block models can also be used for role discovery. The other thing that I was mentioning before is the possibility of compress models in order to analyze which relationship are going on between the different positions in a company, let's say. So what we can see here, which is far clearer than in the basic case, is that the way, let's say, information goes is from blue to red to green, and there is also an internal exchange between blue and red nodes. Okay, so if nobody has question, I will move on to the bigger category of role discovery methods, which is the one that is based on features.
I think Vanjush has a question.
Oh, sorry. Yes, Vanjush.
Hi, I was trying to think of like the first part of presentation. You were mentioning that community detection and roles are complementary to one another.
Yes.
And by that, what can you say if you try to apply community detection in a complementary graph, namely nodes become edges and edges become nodes? Does it mean that the role detection there could be treated as a community detection?
I'm not sure because my concern is that even if you move to a line graph, you still have a kind of concept of proximity embedded in the nodes and the edges there. Whereas what is important in case of roles is that roles might be in completely different regions of the graph. So I'm not talking, I mean, communities have, by definition, an intuition of closeness of nodes, whereas this is not the case for roles, because, I mean, the extreme case is that you can even transfer roles from one network to the other, whereas it does not make sense in case of communities because they might have different densities and different sizes.
Okay, because I was thinking that if you can have like, because in community you are mainly dealing with edges, and that will tell you how much connected the specific cluster is, and then with when you're dealing with community, the way I understand it is that you mostly are trying to like have a node perspective, right, rather than edge perspective.
Yes, to a certain extent, in the sense that when you are talking about roles, what you do is you define a node according to the connectivity patterns it has to its neighbors. But at the same time, in the same graph, there might be another role that is not connected to the first one. And the reason why they belong to the same role is that their neighbors are isomorphic to some extent, but I guess the best definition is role similar.
Okay. Yeah, yeah, I might be wrong, but I just thought like maybe it's possible to do something like on different domain, and then you go back to like, I mean, I don't know, I could be wrong. My imagination was wrong.
Totally, you can take the graph and manipulate it in such a way that, as we're going to see now, you kind of highlight the structural properties and then you do community detection on this new representation of the graph itself. But the important thing is that you need to be very careful when you consider the concept of proximity, because when you do role discovery, the fact that you just look at the nodes you are connected to in 1, 2, or 3 ops, it's really limiting.
But if you go back to a star, you had the star topology right there.
Which one?
Go back to the slides. Back. You had the star topology that you were explaining.
This
yeah,
one?
here, like here, this one. Let's say 1 and 13, they are role nodes, right?
Yes.
But if you take this graph and you compute the complementary nodes, edges and edges nodes, and then what you do there, you compute a cluster of edges, right? Instead of cluster of nodes, when you run community detection on complementary graph.
Yeah.
And then from there, you get those cluster of nodes, and then you go back to the original graph and you try to see where those cluster of nodes go. And can you define the role like that?
I mean, I kind of get where you want to go, but what if you remove node 7?
I mean, the cluster of edges will still be okay, I guess, because the cluster of nodes for the role 1, I mean blue 1, they will not be affected if you remove node 7. But I don't know. I'm gonna have to think a bit more because I don't have a really.
I'm not sure. It's also kind of difficult to me to visualize what you're trying to say. So I don't know. Maybe we can discuss about it offline.
Yeah, maybe. Yep. Okay, thank you.
Okay, so let's go. Oh no, sorry for the spoiler. Okay, so we were about to start with feature-based methods. And this is kind of a big category because they are more scalable than graph-based methods, but at the same time, they're kind of more. It's kind of more tricky to get a good result in this case. The way they work is that they operate indirectly on the graph by transforming the graph in a matrix which represents it in terms of features, where each node is characterized by a value for a set of features that has to be selected. And as a matter of fact, the first step here is to construct a meaningful node feature matrix. Then, once you have this new representation of the graph itself, the way you assign roles to nodes is by, for example, clustering the matrix or doing some kind of low-rank approximation such as non-negative matrix factorization. And here I reported one of the most well-known role discovery algorithms, which is called ROLEX. And the way it works is that for the feature construction phase, it considers the degree of a node and some other numbers that describe the neighborhood of the node. And then once this matrix is ready, what they do is a negative matrix factorization that to some extent is the same as clustering to do this role assignment. But one thing that I would like to stress here is that not all features are good features when it comes to role discovery, because, I mean, first of all, you might have internal or external features, but to go back to the example of the organizational chart, I doubt that if you consider the first name of the employee as a feature, you will actually get some insights on the structure of the company itself. But even if you just consider internal features, and by internal features, I mean, for example, the degree of the nodes, the number of triangles, or the number of one op, two ops neighbors, and so on and so forth. It's kind of tricky to do a meaningful feature selection, and because I mean, not all features are able to capture the structure of the graph itself. But this is kind of unfortunate because the quality of the rows you will end up with is strongly dependent on the quality of the features. And I have an example here, still with the graph that we were talking about before. And in this paper that I link down here, but it's also in the references, what they do is they try to build a classifier for rows according to some structural feature. And what they show is that, for example, if you take just the degree, there's no way for you to distinguish node 7 from node 8 because they both have a degree 2. But it's clear that while 8 is kind of a peripheral node, so 7 is more of a bridge. And in order to get these, to capture this difference, it's necessary to add some more feature. And in this case, what they use is, for example, betweenness centrality, which is computed on graphs as a measure of the importance of each node. And if you look at the orange line here, you can see that node 7 is different from node 8, but at the same time, there is no way for you to distinguish between node 7 and node 1 and 13. So what I'm trying to say is that most probably one feature won't be enough, but at the same time, we need to be really careful with the features that you're using to build the rows, because the result might be really, really different. Okay, so going on, I would like to cover these 6 applications of both community detection and role discovery, and highlight in which cases communities perform better than roles and the other way around. So if we talk about node classification, the main distinction we have to do is, do we assume that nodes belonging to the same class are similar to each other according to some attribute? If the answer is yes, then it's better to go for community detection to solve this problem. But if the answer is no, which means that in the same class there are nodes that might not share the same attributes, it's more likely that you will get better results with roles. And another thing which is really important is that, as I was saying before, communities are defined on the graph on which they are computed, whereas roles are a bit more flexible in the sense that they can be transferred across network, because just to make an example, an hub is still an hub. Then moving on, we have link prediction, which is basically the task of given a graph which we know to be incomplete. We would like to predict which node, which links, which means which edges are missing or might pop up in the future. And as a rule of thumb here is that if you would like to find links that are short range, which means links that most probably are inside the same community in the sense that they connect nodes that already share some neighbors, it's far better to go for communities. Whereas in the other case, if you want to connect nodes that are far away in the graph, or even if in parts of it that are not directly connected, it's better to use role discovery. Then we have anomaly detection, and in the majority of methods for anomaly detection use some kind of concept of roles, because if we take a static network, which is a snapshot of a certain event at a certain point in time, and that's it, anomalies will be defined as nodes that have a strange role compared to the others. Whereas if you have some kind of temporal information, so a dynamic network, it might be interesting to look at the nodes that jump from the one node, from the one role to the other in a way that is kind of suspicious. Then we have the task of summarization, also similar to compression, which I also covered before with block models, but still I would like to repeat it because, for example, if we look at the organizational chart we were using before, if you use summarization, it's far easier for you to realize that these category of employee, let's say the developers, are not directly communicating with the top management.
I have a question. Susanna?
Yes.
So when you do node detection in general, do you look for one particular type of role? I'm sorry, when you do role detection, do you look for, like, let's say just for like hubs or just for like bridge nodes between communities, or you just do kind of an unsupervised collection of roles, of different type of roles?
You can do both of them. But in one case, you assume that you know what you are looking for and which are the properties of these roles that you want to find. Whereas in the other case, you get most probably a richer result, but then there's the problem of how to interpret it, because you just get the information that these nodes belong to the same role, but there's not really a way to automatic label that this role means hub, bridge, or something that we are not even thinking about.
Okay, I see.
Okay, did I answer your question?
Yeah.
Perfect, thanks. Okay, then. One last application is visualization, and even if when you go with bigger graphs, it's kind of difficult to put them on paper, still it's useful to add some information to them according to whether you're looking for communities or roles, as we did before with the example on the organizational chart that I reported here again. Okay, so that's it by my side. The things that I would like to stress is that both communities and roles are useful, and it's important to have the two concepts clear in mind, because they are based on different properties of the graph, and so you don't want to mix them because they are not interchangeable. And while community detection receive a lot of interest, role discovery is still in an early stage, in the sense that, yes, it was explored in social network analysis, but if you want to extend it to other fields, the problem gets kind of tricky, even if there are a lot of applications for which roles are really useful. And I mean, we cover some of them, but there are some others, such as network alignment, which is basically an NP problem, but also role preserving, data anonymization, and so many others. Okay, so here are some references on which this presentation is based, and there are also some good starting points if some of you want to read a bit more about the concept of roles, and I will be happy to answer your questions. Thank you.
Thank you, Susanna. Very nice.
Thank you.
Thank you very much for the... Yeah, go on, sorry.
No, I'm just thinking that there might be many of our RISE fellows in their research agenda might be aligned with the role discovery, whether it will be some insecurity and privacy, finding some anomalies, or maybe interpreting the behavior of the sportsmen. So no, maybe for Thessaloniki people or for Insubria people, that can be very, very much into at least part of their research agendas. This could be also a possibility for collaboration.
Yeah, I mean, it was kind of tricky to pick an example out of IoT dependencies or kind of stuff. So I just went for a more general case. But of course, you can translate it to your domain-specific applications.
Maybe, I don't know, Sophia, I saw that you unmuted. Did you have something to comment on that respect?
Yeah, I just wanted to say that your comment was absolutely right. In a sense, thank you, Susanna, for the great presentation. Because indeed, for the people in Thessaloniki that are doing the analysis, and for my work specifically, role discovery would be very interesting to discover, let's say, user roles in online forums and user behaviors, based on user behaviors and structure of online forum communities. So thank you for the presentation.
Thank you. I see that Ahmed has a question.
I have just a comment on what you said as well. First, thank you for the presentation, and I hope everyone is safe. My comment is for what you have presented. I had a part of my research on that, on community detection, and as an application of it, it's a botnet detection, for instance, peer-to-peer botnet detection, since they create communities. And I will tackle this in my next presentation, and I will because I will present it in 21st of May, and I will make a reference to your presentation, because it's really interesting how botnets create communities, and we run some community detection algorithms on, of course, based on structural similarity and multiple other factors. So thank you for the presentation.
Thank you. And I also wanted to point out that also Ludovico mentioned the difference between communities and role in his presentation on graph representation learning, because even in this case, it's possible to kind of bias the methods to produce results that are more reflective of the community or for the role structure.
So I have a question / comment on this. So typically unsupervised community detection approaches, what they do is that they build embeddings for each node, and the idea is that these embeddings should be able to optimize for the link prediction task, which means by doing something like a dot product between two embeddings, you should be able to tell how likely it is that these two nodes are connected. Now, in a sense, this is a community detection problem, because you expect the communities to have high internal density, so you expect members of the same community to have to be very likely to be connected. So these embeddings have always been used for community detection. However, if we look from the role perspective, we know that the director of a department is less likely to have high connectivity with the rest of the department, but it is very likely to have good connectivity with the heads of other departments, for example. So the point would be, given that we try to optimize for link prediction, and given that link prediction depends on both communities and also depends on roles. So my question is, why is it that these embeddings that we produce by optimizing for link prediction work well for community detection, but don't seem to work that well for role detection? If they really optimize the link prediction task, shouldn't they kind of encode both types of information internally, kind of automatically, without the need for different techniques? Because if they don't account for roles, they will not be able to really solve the link prediction issue that depends on both community and role.
Yeah, I see what you mean. And I would like you to think to the fact that you do like a dot product between embeddings. And the problem here is that most probably you will end up with a nice score if they are connected to the same node. But in the case of roles, since they might be in different regions of the graph, you need a way to say that my neighbor corresponds to your neighbor. So a kind of a one-to-one mapping, which goes back to isomorphism, that allows you to say that those particular neighbors are equivalent, even if they're not connected.
Yeah, which basically brings me to the point: would it be possible to build some kind of embeddings that consider both things? So imagine that we have different departments, and in each department there are some hubs. So, and a hub in a department is very likely to be connected to everyone in the department. So we would have something like when we take two nodes and we want to predict whether they will be connected, we would have a feature that tells us, or a bunch of features that tell us, are they in the same department? And then we would have another feature that tells us, are they hubs or not? And then non-hub to non-hub would have a low link prediction score, no matter if the department is the same or not. And instead, if you have at least one hub among the two, then the score would be high if they are in the same department, but low if they aren't. So maybe it's a matter of how we decode these embeddings. In order to build we should build richer embeddings.
I would add it's also a matter of which features you select, because I mean, it really depends on the task you want to solve.
Yeah, but the idea would be to not select features, but just let the link prediction optimization pick up latent features.
So actually, I would be very careful with that, because if you really want to do both, you might end up with embeddings that are not good for either. Because to some extent, I mean, in maybe first part of your question, that the dot product of embedding actually predicts the link between these two nodes, would be, at least I have interpreted in a way that indeed it predicts a link, but not in the original graph that Susanna was showing, but probably the higher order graph that again comes maybe through the Vanush first comment, that say all the CEOs of all the world from all the companies, they would be then in one specific location, a low dimensional space. That means the predicted links would bring a new graph that all CEOs are connected, and then all managers are connected somewhere nearby, and then a bit further all the developers or whoever else are connected. But the graph on which you do prediction is not the original graph, but some kind of a higher order version of the initial graph, or some kind of a, and then if you want to do, so, and that would be the interpretation of what is a link prediction. So not, so on the other type of graph that you have to either explicitly or implicitly sort of have in mind. But if you want to do, to take into account both features, both community features and the role features, and then produce one embedding, I am not sure that is a very safe path. Maybe, but maybe not, because then you might be in the worst of both worlds, because you will neither predict well the communities, nor will be good in the roles. I don't know. Maybe Susanna, you think differently, or maybe Ludovico, you have some, you meant something else.
I mean, I totally agree that you must be careful if you want to do something in between, because I'm not really sure how much you can capture. But as you were saying, most probably, like all the other cases, it comes back to modify the graph in such a way that you can highlight either communities or roles or both of them.
Yeah, just that because there are probably some applications that only need the communities and some applications that only need the roles. But I guess, like, for example, just doing a link prediction on the original graph requires both to be done correctly and to be done very accurately. Using only one of the two information will not provide you good link prediction. So I guess there are plenty of tasks that would be better if you have both kind of informations. And then the point is, how do you mix them together in the right way? That's the harder question.
Yes.
So in a sense, that's what our postdoc in the group, Zacharias, was doing in the last paper, was one option is to produce several embeddings for the same node. and then you can be more sense. You can produce, say, 3 embeddings for different roles and 5 embeddings for different communities. And then you are, every node is then defined by, say, 8 some kind of identities that are good for certain tasks.
Yeah, that could be a path forward. But yeah, I feel now it's becoming more of an internal KTH discussion. So if someone else has other questions, please feel free to.
Yeah, I have a question.
Oh, go ahead.
Okay. Can I ask my question, or is someone else?
No, go ahead. Then there's
okay, it's just because in the slide when you talked about feature-based method, it seemed that it was more like it was similar to graph representation learning, but instead of having a feature vector for each node, you will have an embedding for each node, and then you can apply a classifier algorithm to detect the roles of the nodes. Okay.
Yeah, I mean, it connects back to graph representation learning, of course.
Yeah, but then you said, you answered to one of the questions, you can use that to detect communities or roles based on the set of features you select, right?
Yes, I mean, some methods for graph representation learning are most biased toward giving a community-based representation, whereas some others are more on the role-based version of it.
Can you give examples, like what kind of features I can use for if I want to do community detection, and what I can use for role-based?
I mean, for roles, as I was showing before, centrality is a good starting point because it already gives you some kind of a measure of the importance of a node, whereas if you are more looking into communities, you can, for example, look at the number of triangles that connects back to the clustering coefficient. So how well you are connected to your neighbors.
Okay. One more thing, how you can do you have like ground truth labels for the rules?
I mean, there are not that many other data sets out there, but there are some. And I mean, for example, for organizational charts, there are a few of them, including the famous email network of Enron. But the thing is that most of the methods are still kind of be tested on toy graphs because, I mean, role discovery outside of social network analysis is still at an early stage. So they do some kind of validation, real world data sets, but not that much. Also because of the lack of good data sets to be analyzed.
Okay, I see. Thank you.
Yeah. So I think
Can I ask a quick question?
Yes.
So this using this graph embedding, so the community detection can be like a hierarchical community, or like a joint sort of overlapping community, or there are many different community detections in general. But with using graph embedding, can you actually get hierarchical community structure? That's
I think it's possible, but since the expert of representation learning here is Ludovico, I would ask for help.
Oh, okay.
So the idea is that typically when you use graph representation learning, you end up with these embeddings, and then it's up to you how you want to decode these embeddings into some kind of machine learning answer. So if you want to do community detection, you might have classification-based decoder, which basically takes this embedding and goes through a small machine learning network, and basically gives you as a result the community labels. So it's up to what you put as output for training this decoder step. So if you train this decoder step with, for example, a multi-label, so you can have multiple communities for each node, and that would be overlapping communities. And for hierarchical communities, I guess you could also come up with a way to train this decoder to output that part. And then depending on which graph representation learning technique you use, this backpropagation for the training might even go to backpropagate to how the embeddings were generated. And then you might have embeddings that are trained on purpose to give you the right community assignments. So it depends basically on how you train your classifier.
I see, that's cool. So like the community detection is one thing, and role discovery is another thing, right? So when you think about this, like a university, and there is a president and a department, and so do you think essentially those structure information, head of department connects to the other head of department? So role is there, which is existing in any case, but the structure of community-wise, it's kind of hierarchical structure. That kind of thing is essentially possible to detect using graph embedding, like representation learning, right? That would be cool to me. Anyway.
I think it might be possible. I mean, I never done this, but I think it's definitely possible if you train, if you find a good way to train this machine learning based decoder, then it's absolutely possible to find it. So the typical problem is that if you go with non-overlapping communities, you might end up with each department being a community, except for the head of departments, who somehow end up forming a community of head of departments. But if you allow overlapping communities, then you might end up with each head of department being part of a community that is his department, and another community which is the community of all heads of department. So it is possible to have this kind of structure. However, if you then want to find something like I have departments and then schools and then the whole university, for that part, I guess for that it would be the easiest way would probably be to train multiple decoders with a different granularity in terms of labels, and then you might have a low granularity decoder that gives you the schools and a high granularity decoder that can give you the exact departments.
Okay, great. So interesting. Thank you for presentation and Q&A.
I think Vanjush has a question.
Yeah, I was thinking now that usually when you do community detection, you can rank the connectivity of each community. I mean, how much connected one and the other, or with respect to the other. Can you do some ranking of nodes, let's say hubs, when you do a role detection? I mean,
it's I'm looking into it, but I wouldn't say there is a number that allows you to quantify the quality, as can be done for communities, for example, with modularity, average degree, edge cut, and that kind of stuff.
Okay, because usually, I mean, I used to work a bit with a Laplacian matrix, and there you do get the variance of the positive values and the negative values for like two cluster partitioning. And then you see the first cluster has much lower variance because the variability of positive values, it's much lower compared to the variability of negative values. And I think should be some analogy there, but I still can't imagine how you construct a loss function in nodes to think a bit more about that.
But I mean, it might be interesting to look into it because, yeah, we would like to have a measure of role quality.
Okay, and I don't know if I mean that's a good research, not just for like people in Greece, but I guess also for race folks. I think Krista would like to hear some to hear it and see if there is some untapped potential for our company, because we have a lot of data and communities, I guess. So there is.
I hope that Susanna, I think you have intended to have a RaceFox collaboration.
I have an intention, but still I have.
Yeah, so
I'll talk to you later.
And anyway, at least people who are in Stockholm and who are coming to Stockholm, I believe, regardless to whether you come to RaceFox or KTH, we can always discuss these issues.
Okay. Okay, thank you.
Thank you.
So are there any more questions?
Just a last thing. This is an unsupervised learning technique, role detection, right?
Yes. So the one I presented, yes, but you can kind of tune it for the supervised methods if you already know what you're looking for.
Okay. Okay, so it's good. It's easy to incorporate some like labels or prior knowledge or anything. I hope. Okay, can you hear me? Because I think I lost connection.
Oh, could you repeat? I didn't get the answer.
No, I think like I mean the existing methods are probably hopefully easy to incorporate prior knowledge or labels or anything.
Yes, for sure.
Okay. Thank you.
Thank you.